So I'm going to be giving you an update, not on exports, but on plankton, aerosol, cloud, and ocean ecosystem, which is NASA's new ocean color mission that is scheduled to be launched in 2022, late 2022, potentially 2023, depending on any upcoming government shutdowns. So this presentation is more an entertaining presentation, not so much hard and technical numbers that will be appearing behind me. So if you really want to listen about gory details, come and find me at the PACE poster. I can bore you down, but I think it's kind of much more important to kind of get you guys excited about this because it's a pretty cool thing. So how does one make a mission? You know, you kind of start thinking about some kind of overarching science objectives and start asking like questions, you know, what do you want? What do you need? So first, you know, we want to be able to extend these key systematic observations of the ocean that tend to tell us something about biology, biogeochemistry, and ecology. But also, like, since we're like an atmospheric mission, we have to kind of pay attention to aerosols and clouds. And then we want to make a step forward, you know, kind of start making new things that can allow us to study the carbon cycle and oceanic ecosystem as it's changing with the changing climate. And ultimately, we want to be able to collect good information. Did I turn on that light? Because it seems every time I move somewhere, the light turns on. I'll just stay here. So we want to be able to collect really good information in aerosols and clouds because aerosols are actually the biggest amount of uncertainty when it comes to understanding the radiative forcing on a climate model. So we really want to learn a little bit more about that we know right now. And ultimately, you know, if you want to make this atmosphere ocean mission, we want to be able to understand interactions. How does the ocean like impact the atmosphere and vice versa? So when you have these things in mind, then you start thinking, what can you make? And so what we're going to be producing, and these are the required things. These are the things that we're already producing. This is a list of these products that we're going to be making from PACE. And they might not look really cool to this community, and you're going to be recognizing chlorophyll. That's cool. But actually, you can translate them into something much cooler. And these are the things that we want to make. These are the advanced products. This is where we start talking about the carbon stalks and carbon fluxes, phytoplankton pigments, the diversity of the phytoplankton from space, productivity, you know, so many different things, and probably some of them that I forgot to mention. This is what we're looking towards in PACE. So PACE is building on the legacy of these fantastic instruments that have been flying up in sky since 1978, since I was like 1 year old. And these missions told us so much more, I mean, so much. We learned so much about the global distribution of the algae in the ocean, how does the ocean function, and things like that. But also, these platforms these missions had some shortcomings. And these shortcomings is something that we also build PACE on. PACE is going to include 3 different instruments. First one is a hyperspectral imaging spectrometer. God. And 2 multi-angle polarimeters. You see, that's why like, it's easy to give exports because, wait until I get to acronyms. You're going to see it. It's really bad. So these are 3 instruments that PACE is going to be carrying, and that's going to allow it to produce all these parameters that I was telling you and focus on advanced ocean color products, different things from different information about the aerosol particles, clouds, as well as lands, because land people always slide on our missions. If they were on our mission, they would be called PLACE, not PACE. That's our current joke, but it doesn't really ring bell with this community name of mine. So we are cost schedule, which means we have $805 million to build this mission. It's going to have a fuel for 10 years, but always designed to last 3 years, which means it's just bureaucracy. We're hoping it's going to last the same number of years as MODIS and CWIS, who are also designed to last only 3 years. It's going to be orbiting at 675 kilometer altitude. Altitude is going to have ascending orbit, and it's going to pass near closest place in the equator around 1 p.m. Solar time. So going back to that little schematic that I built here, you can start looking at these legacies and see what you can change, what you can make better. So I'm showing you here 2 different images, one from Arabian Gulf here, and the second one off the coast of Libya, so Mediterranean Sea. And here I just highlighted different problems or different issues that we have using current ocean color satellites. And I'm going to just walk you through different things that PACE is going to be able to do to overcome the problems that we currently have. So PACE is going to have the same pixel size as current ocean color satellites by increasing the spectral resolution, which is pretty cool. And then you can start using that spectral resolution to start differentiate different algal groups, like in this situation where we have a diatom bloom intermixed with Noctiluca bloom in the Arabian Sea. You can start looking at these infrared channels to start discerning different characteristics about the aerosols, start improving your atmospheric correction, but also learning something about aerosols. You can start tilting your satellite to stop losing the data due to the sun glare that you can see this here. And then ultimately, you can use the instrument performance requirements, such as build your instrument in a smart way, so you'll start getting these image stripes that you might see in, I don't know, for example, Mary's data. They're really, really bad there. And ultimately, in order once you launch a satellite, you really can't go and fix it anymore. So you just have to keep an eye on your calibration. We're going to keep on doing that using the twice-a-month lunar calibration and onboard solar calibration. And ultimately, we're going to have this multi-angle polarimetry, which is going to be super, super awesome because it's going to give us so many information about aerosol properties, but as well as cloud properties, and potentially something new about ocean. So if I walk you through these instruments, the first one is Ocean Color Satellite instrument, which is the workhorse, and that's what you guys should be excited about. And this is why. So we've been stuck with limited spectral resolution for some time. If you look at the CZCS, which is a long time ago, CWIS, MODIS, and VIRS, if you look at this visible spectral, UV spectrum, but this is the area where we usually operate, you have these thin stripes. And currently what we have flying up here is MODIS and VIRS. And they have either 7 or 5 different bands. So think about your spectrophotometer that you have in the lab and all that spectral resolution that you get. And I rip that all away and you have those 5 data points. You won't be able really to see a lot about your processes. What PACE is actually your spectrophotometer in space, pretty much. So what does that spectrophotometer give you? Let's go back to that Arabian Gulf, that Noctiluca and the Item Bloom. We all know that's not the same thing. One are good, one are bad. One are yummy for fish, one are not yummy for anybody except for turtles. Nobody cares about turtles, and they're not important for the carbon cycle, so we like diets. Anyways, if you take your spectrophotometer and measure the absorption of these species and put the lens of a VIRS, which is the current ocean color satellite, you get these 5 dots. You can't really see what the difference. Now, there's like some difference here, but that's not statistically significant in our world. But if you put the lens of PACE, you start seeing this resolution that's going to allow you distinction between algae that are important for the ecosystem, for the carbon cycle, and algae that are just nuisance and really kind of big problem in Oman. How does it look like? This is how the ocean color instrument looks like. I have not, I mean, it's not yet assembled, but when it's going to be assembled, it's going to be kind of my height, not my weight, but you know, let's say my size is going to be all built in NASA Goddard. It's a cross-track 360 degrees continuous rotating telescope. The hyperspectral parts is in this area, which is it has 2 slit grading hyperspectral spectrographs. The infrared portion is pretty much fiber coupled multiband filter spectrographs, and this enough about technical stuff. All these together are going to be allowing us to see that beautiful spectral hyperspectral resolution and that achieving that aerosol composition and better atmospheric correction in an infrared spectrum. When it comes to the polarimetry, they're going to be sitting here in PACE. They're actually a value added. So why do we want to look at the polarimetry? So think about having your sunglasses, the polarizing sunglasses. They're pretty cool because, make the world a different place, a much better place if it's really, really sunny. But polarization actually in the natural world offers us a view and additional information about the world around us. You can, take a picture of the total intensity of light and then look at the, polarized intensity of light and then look at the ratio of these things. And this is a completely new set of information that opens up some worlds that you have really never seen before. And then you can, for example, in our case, use that information to start tracking the aerosol, understand their composition, and many different things. They're really important to bring that information back to these big Earth system models that need this information because we just don't have enough information, the global distribution of these different types of aerosols. These both polarimeters were not part of the original PACE. And they're a contributed instrument. That means somebody came and gave it to us for free. The science capabilities were defined by the instrument teams, and both of them are actually originally decided as a cube scale type instruments, so which means teeny, teeny, tiny instruments that you can shoot in space for really cheap money, which is not what they would do in NASA. But anyways, specs come from Netherlands. That's the one on the bottom that looks like a Lego. The one on top is HARP2, and it comes from University of Maryland. This is some gory details about HARP2 and Specs 1. But it's really important to understand that HARP2, the one on the top, has a multi-angular system and really wide swath. While Specs 1 is going to have a hyperspectral capabilities and really narrow swath. So if you put all these 3 things together, you're going to have, in every passage of PACE, you're going to have 3 different sources of information, like gigantic amount of information about 1 pixel. And there's so many cool things to do with it. So when you start looking at the synergy, Specs 1 is going to be probably used mostly for aerosols to understand different characterizations of the aerosol. But you're going to extend what we actually were licensed to do as part of the OCI for aerosols. When it comes to HARP2, it's going to do the same thing for the clouds. It's going to help us understand much better how the clouds are distributed, type of clouds, the type of these droplet size and ice particles in the clouds. Is going to extend what PACE, what OCI can do when it comes to clouds, but it's also probably going to help us improve our atmospheric correction. And atmospheric correction is something that's really, really boring, but it's really important because it's 90% of the data that comes to the satellite. Without good atmospheric correction, we can't see the ocean. But when you combine all these three things together, you have the largest amount of data that pretty much the world has ever seen targeting oceans and atmosphere. And you can start thinking about new products. You know, like we have some ideas how to start looking at the ocean color using this polarimetry. You know, we know really well for some of the work of our colleagues that some ocean particles do polarize light. Can we start doing things like that? Maybe some new products such as wind speed, but please don't ask me about wind speed because I have no idea how they're going to do that. But somebody can do it, obviously. So where are we in this story? Laura just a second mentioned KDPC. So when you work at NASA on a mission, you have to have an idea, you have to have questions, you have to have an instrument, then you have to have acronyms, reviews, and charts, because that's how they refer to a slide. So we just passed the PDR, which is a preliminary design review. No, you see, acronym, review. And that allows us to step towards KDPC. KDPC is key decision point, which allows us to step in the next part of the mission. This is where they see, okay, you guys have done everything is cool, you're proceeding as normal, just continue. And KDPC, this phase C that we're going to enter in, hopefully in August 15, it actually becomes pretty cool. When it comes to the size of the mechanics, you know, like building and stuff, they're going to start assembling things, and all the different portions of the mission actually have to pass this critical design review. Again, acronym CDR. Then, before that one, is going to be a series of sub-element engineering peer reviews, or EPRS. It's awesome in our meetings. It's just like it's flying everywhere. But when it comes to science, this is where really cool stuff starts, where you guys can be involved. You know, on the science team, so I'm part of the science team, I'm their biogeochemist. We're going to start responding to the element issues because the design of the instrument has to be finalized. We're going to be able to kind of do these little teeny tiny studies to see what we can actually do. And then we're going to implement science capabilities, what is space actually going to be able to do, and then interact with newly formed science team. After that one, if we pass KDPD, we can assemble the system and shoot the rocket in space, and then we party, no? And then we do science. If you don't want to wait until then, you can come and play with us. There's mission application plan. Every NASA's mission has to have an application plan. You can go on our website and read Space Science application plan, or just corner Maria and ask her about it because she is the deputy there, and she can tell everything about how you can get involved. And just to once again reiterate, there's a call for Space Science and application team. Deadline is June 15th. And you can bug Laura, but Paula Bontempi would be your point of reference. You can learn more about PACE on our website, where you can download all these beautiful technical memorandums that's going to tell you everything about history of PACE and all different science studies that we have done in order to develop this mission. And they're pretty cool, actually. Some of them are cool. Some of them are just math. And then you can, I mean, I'm honest, you know? You can learn more about PACE on our website. We have really like a strong outreach component that I've been trying to entertain you a lot. I don't know, how many of you did take phytoplankton quiz? Oh, people. Okay, everybody. Go on PACE website, click on this button, and learn which phytoplankton are you. Please come and let me know. I'm going to give you something really cool. Come on, really. How can you survive without that? It's a millennium clickbait. Anyways, just in the end, okay, this is really more entertainment value, but my role is to be biogeochemist, write papers, and entertain people and encourage them and excite them about this mission that is really coming, and it's awesome, no? If you want to learn once again about gory details, come and find me. I can really go completely technical engineering. But in the meantime, just kind of like think about PACE, that this is the first time in 2 decades that our science community has an observatory they can grow into, you know? It's not something that is predetermined. We don't know what's going to be out there. We know there's going to be unprecedented global views of ocean and atmosphere, but probably so much more. So with that, thank you. I have 24 seconds. I can answer a fast question. No? And now, Dave Siegel. Questions? No. Please, no, find me at the PACE. I can talk really like, you know, science, engineering.